Today, we want to practice that shortcut that I said very little about last time. In fact, I only just did some problems with the shortcuts. Some of you knew the shortcut, and everybody else is like, oh, whoa, how did that work? It's not a magic trick. Actually, if you don't know, I guess it is kind of a magic trick. And I want you to be able to describe that process for finding the derivative of a function, or sorry, the derivative of x to the n in equation forms and in words. So once you do that, please take a moment and find these 9 derivatives. Pause the video now so you can take a moment and find those 9 derivatives. Welcome back. First, we want to describe finding the shortcut for finding the derivative of x to the n. Would anybody like to volunteer their shortcut, either a description of their equation or a description in words? What you got? Ax to the a minus 1. In this case, I'm using n, so nx to the n minus 1. That works. That would be our shortcut described in symbols. How would we describe that in words? What's the process that's going on here? Nx to the n minus 1. What do we do? Someone else wants to describe this in words? That's why it's easiest to jump on the first one, because if you remember nx to the n minus 1, that's the one that you want to say. How do we describe this in words? What do we do? Break it into 2 steps. What do we do first? Where's that n come from? That's just the exponent. So the first thing that we did was we took the exponent and we just multiplied by the exponent. A lot of times this gets read as bring down the exponent, which is terrible because I look for the bring down button on my calculator and it's not there. There's no button that says bring down. What we're doing is we're multiplying by the exponent. So multiply by the exponent. And what do we do after that? We subtract 1 from the exponent. So those are the 2 operations that we perform to make this derivative thing happen. Subtract 1 from exponent. Now, we did not justify why this works this way. To do that, we would have to grab our definition of the derivative and see if this is what happens. We don't want to do that right now. We just want something that works. Let's think like engineers and not think like mathematicians. Let's think of like engineers. Like, oh, we've got a thing that works. Mathematicians be coming along and saying, hey, how does that work? And engineers are like, oh, I don't know, it just works. Now I'm going to go build a bridge. Mathematicians be like all in the philosophy department, what is a bridge? And then the engineer's like, oh, we've got work to do. And the mathematician's like, oh, I have think to do. So excellent. Now let's put this in play and see what kind of assumptions you made along the way. The first one we did in the warm-up, what is the derivative with respect to x of x cubed? Anyone have the first one, the derivative with respect to x of x cubed? What's the derivative of x cubed? Go ahead. 3x squared. We did that one in the warm-up, so good choice. Just a quick note that d over dx says take the derivative of whatever we have next. So this says the derivative of x cubed is 3x squared. In function notation, we would first say our function, let's say f of x. If f of x is x cubed, then the derivative is 3x squared. We could write f prime of x is 3x squared. But when we write d over dx, we're just saying the derivative with respect to x of, then whatever comes in. Any questions on 1? How are we doing? Good. Everybody 1 for 1 so far? Now I'm messing with you. What about 5x cubed? I totally did not discuss how this should work. I wanted you to just guess how it should work. Anyone have a guess? 15x squared. Who's got 15x squared? How did you know that? I didn't tell you that this was a linear operator. You just took that 5 and said, well, I'll just multiply the 5 by 3. That's what the instructions say. Multiply by the exponent. Excellent. So if there's a constant that's being multiplied, we just carry that along. So we're reading this as 5 times the derivative of x cubed. We had to guess at what to do with the 5. We just multiplied it, and it makes sense because the coefficient in problem number 1 was 1. We multiplied that by 5, or sorry, by 3. And the coefficient in problem 2 was a 5. We multiplied that by 3. How about number 3? Oh, how are we doing? 2 for 2? 2 for 2? Some of you are like, oh, am now. You're like, oh, is this a quiz? And I'm like, oh, kind of. And then you're like, oh, then yeah, 2 for 2. Full marks, man. All right, someone else. What is the derivative of 5x cubed plus 7x? Anyone have this one? What do we got? 15x squared plus 7. That's excellent. I gave you 2 terms, and your natural inclination to think linearly took over and said, well, these are just added together. Why don't I just add the derivative of each term? And it works. The derivative is a linear operator. Derivatives respect scalar multiplication and function addition. So you read this as the derivative of 5x to the third, and then the derivative of 7x. Moreover, the extra thing that was going on here, when we read the 7x, we were reading that as 7x to what power? To the 1 power. So we multiply by the exponent. 7 times 1 is 1. Subtract 1 from the exponent. 1 minus 1 is 0. X to the 0, we don't have to write. X to the 0 is 1. So you read this as 7x to the first, and we remembered that x to the 0 is equal to 1. How are we doing? 3 for 3? I didn't tell you that it was a linear operator. You just said, nah, let's see if this works. Then you checked on Wolfram Alpha, and Wolfram Alpha was like, oh, high 5. I wish Wolfram Alpha was that cool. It just like spit out stuff. Now we start playing a little bit more algebra. Oh, I guess I'm not going to write the radical part. We've got a cube root of x. I want to write that with an exponent. What is the exponent with a cube root? Not negative 1/3. The x is in the numerator, so it's a power of just 1/3. Negative 1/3 is the next one. What we're trying to get out of these exercises is that if we can write a bunch of powers of x, terms with powers of x, then we should write terms with powers of x, because then we get to do this easy maneuver. Multiply by the exponent, subtract 1 from the exponent. So with this x to the 1/3, what's the derivative going to look like? Who's got this one? One-third x to the what power? Negative 2/3. Multiply by the exponent, subtract 1 from the exponent. Multiply by the 1/3, 1/3 minus 1 is negative 2/3. Awesome. How's everybody, okay? Did anybody simplify this? 1 over 3 cube roots of x squared. I mean, it's okay if you did, because you're like, oh, the problem was presented in radicals. Maybe I should answer in radicals. I want to flex my awesome algebra skills. I'm fine with negative exponents. I'm fine with fraction exponents. My focus is getting the calculus part in play, and the prosecution will stipulate that students remember their algebra or just need brief reminders about algebraic stuff. We got time for one more, maybe two. We've got the derivative with respect to x. What am I going to do with 5 over the cube root of x? What is this one going to look like? What's the exponent on the x going to be in this case? Negative 1/3. What about the exponent on the 5? Now, what's the default exponent? 1. The 5 is not part of this cube root business. It doesn't have a negative exponent. So we've got to read that as just a regular 5. It's the x that has this negative 1/3 exponent, not the 5. If I wanted the 5 to have the negative exponents, I would have had to put parentheses and around it. I have to include it in some fashion, but it's not. It's just a 5. So what's our derivative going to be here? Negative 5 over 3 x to the negative 1 1/3 or negative 4/3. Excellent. We could simplify that, put the x to the 4/3 in the denominator and write it as x cube root x if we want to be fancy and simplify. I suppose if we wanted to be more fancy, we could rationalize those denominators. But I've already said that I'm okay with radicals being in denominators. We have calculators for that kind of business. We got one more here. Let me do one more because I got room for one more, if not time for one more. I have the derivative with respect to x of 5x to the 3rd over the and x to the 1/3. Notice that if I keep writing over the x, it's a 1/3 x in the denominator. So I want to write this as 5x to some power. What's that power going to be? So we have 3 is a 9 over 3, and we'll subtract a 1/3 from that, and we'll get 8 over 3. Sorry. 9 over 3 minus 1/3, 1 over 3 is 8 over 3. So this will look as a 5x to the 8/3. 3 minus 1/3 is 2 1/3. So this is going to be 5x to the 8/3. Notice that I just did exponent business. I didn't multiply by the exponent. I didn't do my derivative process. That's why I'm still writing d over dx. The subtraction is 3 minus 1/3 is 2 2/3, which is 8/3. And so what is the derivative? 40 by 3, x to the 5/3. Subtracting 1 from 8/3 is subtracting 3/3 from 8/3. So that leaves 3 more that we didn't cover. And there's more than one term, but there's also extra stuff going on. Oh, I put x minus 3 to the 3rd. Kind of a jerk move on my part, but that's all right. On number 7, number 8, and number 9, there's a mix of multiplication, exponents, and addition, where I suggest we think about the distributive property. So next time, we'll look at 7, 8, and 9. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing. Yes.
I took a picture of the
Ah, nice
page.
guy. Sure.
So you forget about it.
What's that?
You forget about it.
Oh, thank you.
Because you extract.
Oh, I pulled out the X. Yes.
You extract.
It's a cube root of
this
X
is
to the
new.
fourth.
Do I need to into the campus?
Once you register on WebSmart, then you'll be
I-
added to the Canvas roster.
Register on the campus.
You don't have to do anything separate. It'll be
Oh,
on,
yeah.
it'll show up on your Canvas.
Thank you.
On exams and stuff, like for the final answer, which one do you go? Between these two fractions?
Yeah.
For like the X power, so just.
Yeah, fraction exponents is fine. Negative fraction exponents is also fine. The previous day
Yeah.
was.
Oh, yeah.
Yes. Yeah, the question will work.
But like, I get a different answer.
I'm fine.
Hi, Professor.
See you later.
All right, then.